All right, let's jump back into polar curves, and this time I want to talk about areas and arc lengths of polar curves. So here's a little example. Suppose we had the polar curve r equals 4 cosine of 2 theta, which I just threw that into Desmos and grabbed this little graph here because that is a rose with 4 petals. So that cosine of 2 theta generates that rose, the 2 theta, since it's even, generates 4 petals, 2n petals. And we have a graph that looks something like this. So pretty little rose with 4 petals. And what if we wanted to find the area that is enclosed by that polar curve? So what if we wanted to know how much area is enclosed inside that rose or those 4 petals by that polar curve, 4 cosine of 2 theta. So how would we find the area? How would we find, or maybe we wanted the arc length, the length of that actual curve as it goes around and around. What if we wanted the arc length of this polar curve, or maybe just the arc length of 1 petal? Right? Or 2 petals. So how do we do that? And that is, again, taking 2 concepts that we've already talked about at great length and applying it to our polar curves. So how are we going to do that? To do that, we are going to first come up with a formula, and it's very similar to how we came up with a formula for our areas in the rectangular coordinate system. We used rectangles to estimate what the area would be, and then we let the number of rectangles go to infinity and turned into a Riemann sum, which was an integral. So we're going to do the exact same thing here, except we're going to be looking at, because we're in a circular coordinate system, we're going to actually look at how do we compute the area of a sector of a circle. So, you know, the polar coordinate system I think of as a circular coordinate system. We're rotating around a fixed ray, rotating an angle and moving from an origin along a radius. So we're talking about a circular coordinate system instead of a rectangular coordinate system. So we're going to look for areas. We're going to take whatever region we're looking at, we're going to divide it up into a bunch of little sectors and figure out what their areas are. So we're going to use the area of a sector. So the area of a sector of a circle is 1/2 times the radius squared times theta. That is how we calculate the area of, and where theta obviously is in radians. So this is how we compute the area of a sector of a circle. And so if we had a region, let's just call this squiggly little region right here. This is our region that we want to figure out the area of in the polar coordinate system. It's defined, that squiggly line right there is defined by r equals theta, f of theta, r equals f of theta, and it is bounded by theta equals a and theta equals b. Now, we are going to make some assumptions here that we are going in an increasing, this is telling us that we're actually going in an increasing theta, that theta is increasing. So b minus a, and b minus a is greater than 0, which means it's increasing, and once through the circular coordinate system, since it's less than 2 pi. We divide that interval from a to b up into n little subintervals. This should seem very familiar. It's been a bit. We didn't do as much of this in chapter 11 with the sequences and series, but we're doing it now again, where anytime we want to know something unknown in our coordinate system, we break it up into little pieces and figure out what the area of those little pieces is, then add them all up and let the limit go to infinity. So that's exactly what we're going to do. We divide this up into a bunch of little subintervals, choose a tag on each little subinterval. So we're basically coming in here, if I could do this with my red, and we're bringing in a bunch of rays, you know, our theta, here's theta sub 0, theta 1, theta 2, and so forth. And on each one of those rays, we are coming in and computing the area of that sector. Okay, and so the area of the sector of each little sub interval is going to be 1/2 f of theta sub I star, the tag we pick on that interval to represent the radius, squared delta x, because, or I'm sorry, delta x is delta theta, and then the total area, of course, is a Riemann sum, and we take the limit as n goes to infinity of that Riemann sum, and it becomes an integral. And so here is kind of the meat of our area formula. and we can put that into just a nice little formula here and say if we have a polar curve r equals f of theta, and we want the area of the region that is enclosed between two rays from theta equals a to theta equals b, and we are making that assumption that a is less than b and that that difference is positive. Again, this is meaning that we're going in increasing order and we're going once through the circular coordinate system. So we're in increasing order of theta. So A is less than B, increasing order of theta, and cycles only once. Okay, so we'll talk about that in just a second in an example how we guarantee that. But we're in a circular coordinate system, which means that we can repeat and our curves can cycle back over themselves. Go back to that rose that we looked at. That rose that we were looking at is cycling through those petals an infinite number of times if we let theta go on and on forever to infinity. And so if we restrict it, it completes that curve from 0 to 2 pi. So if we wanted the area, we want to make sure we're looking at it from just 0 to 2 pi. Otherwise, we're going to continue to gain more and more area as the theta increases past 2 pi and starts to repeat. Okay, so the area is the integral from a to b of 1/2 of f of theta squared d theta, which in kind of shorthand gives us this nice little compact formula. The area is just the integral from a to b of 1/2 r squared d theta. And that's how we calculate area. So let's do it. Let's actually do an example. And I brought an example here. Let's get it. Here we go. Okay, so let's start with this one. Let's determine the area of the inner loop of the limicon of r equals 2 plus 4 cosine of theta. And we don't have the bounds here. I didn't give you the theta values. I just said of the inner loop. So sometimes we're just given some instructions of which portion of the curve. We don't actually want the area of the entire curve. We want the area of just the inner loop of this particular shape. And it is a limicon with an inner loop. So let's get that graph first. So if we're looking at this, this is r equals 2 plus 4 cosine of theta. If we want to graph that polar curve, I like to graph the r versus theta curve here. And so let's jump in here. I already got it set up ahead of time, my coordinate system. And so this is the shift up of 2, cosine curve shifted up 2 with an amplitude of 4. And so we're going to have, we're going to start actually up here. Start up at 6 and let's plot out all my points here and then we'll put the curve in. All right, so we're gonna dip down all the way down, back up. And there we go. So there's one cycle. Now, something kind of interesting is going to happen right here, and we'll talk about where those intersection points with the theta axis are in just a second. But first, let's get this graph. So keeping in mind as we do this, actually, you know what, let's find those points right now because it will be helpful to know where those points are when we get over to the graph. So those particular points right there where it's hitting 0, if we wanted to find those intersection points, find when r equals 2 plus 4 cosine of theta actually equals 0. When do we actually hit that theta axis? When is the r value equal to 0? So that's going to happen when the cosine of theta equals negative 1/2, or when theta is equal to 2 pi over 3 and 4 pi over 3. Okay, so that does help to have those 2 points there. So let's put those in red here. So 2 pi over 3 and 4 pi over 3. Okay, knowing those 2 points right there is going to be useful. So let's come over here and let's even identify them. Identify those 2 rays right on my graph here. All right, so now let's get in there and let's plot this. So we start at 0, we're out here at, let's do that be 1, 2. I'm going to zoom in here. I'm way too far out. 1, 2, 3, 4, 5, and 6. And we're actually starting at 6. And notice that from 6, when we get to pi over 2, we're going to be at 2. So as we're coming down this curve here, by the time we get to 2 pi over 3, we're at 0. And then when we get to pi over 2, we're at 2. So we're going to be here and then in here. And so this curve is going to come in and look something like that. Then at 2 pi over 3, notice that we actually go negative until we get to pi. And at pi, when we're actually at this pi right here, we're at -2, which means we're going to be reflected through. And so when we're coming through this little region here from 2 pi over 3 to pi, we're reflected through actually over here into this region. We're reflected through the origin, and we get more and more negative until we get to -2. And so that means that we're actually going to have a graph that looks something like that. It's spinning through there. And then again, until we get to 4 pi, we're going to do the same thing. So in this little region here, oops, wrong region, from pi to 4 pi, we're going to actually be reflected, and we're going to be looking at that curve up here. And it's going to come up and loop back around. And then from 4 pi over 3 all the way back out to 2 pi, we are going to, let's see, I got to plot one more thing here right there. We're going to come down, around, and back. Okay, let's fix that a little bit. Make it look a little better if I could. Okay, all right, so we've got our polar curve, our limicon, and the area that we actually want is this area in here. So it says calculate the area of the inner loop. So how do we calculate the area of the inner loop? Well, where was that inner loop traced out? The inner loop occurred between those two bounds, between theta equals 2 pi over 3 and 4 pi over 3. So we actually know where that inner loop occurred. The inner loop was being traced out by this polar curve in between the two rays, theta equals 2 pi over 3 and theta equals 4 pi over 3. So those are our bounds. That tells us those are the bounds that trace out the region that we want, the region of area requested. So those are the bounds. That's my A and my B. That's where we're tracing out those, the region that we specifically wanted. So, and that is, just keep in mind that this would be our A and this would be our B. There was the requirement that A be less than B, and that we were between 0 and 2 pi, which we do. We are guaranteeing that right here. Okay. All right, so, and that being between 0 and 2 pi, you can actually use, you could actually even use negative angles if you wanted to, and sometimes we do, and I'll explain that in a minute. The requirement that we be between 0 and 2 pi is that we're only cycling once through the curve, that we're not repeating area, we're not repeating arc length of the curve or area of the curve. So we'll talk more about that little piece in a second. But we've got the two bounds, they meet the criteria, and so we're ready to find the area. And our area formula, just to rewrite it here, is going to be the integral from theta equals A to theta equals B of 1/2 r squared d theta. And so we will find our area here by taking the area from 2 pi over 3 to 4 pi over 3 of 1/2, and our r, 2 plus 4 cosine of theta, quantity squared d theta. And then we're going to finish finish that guy out. We're going to expand it. Did just want to quickly mention that there's definite symmetry here, and you are welcome to apply symmetry and look at this and say, I'm going to just trace out half of that. That inner loop is definitely symmetric. If I find the area of half of it, I could double it. All those same things that we did before when we talked about area in the rectangular coordinate system, we can apply in the polar coordinate system. So I am not going to do that. I'm going to just follow it all the way through, but do know that you could if you wanted to make some of those little adjustments. So this will be 1/2 2 pi over 3, 4, 16 cosine theta plus 16 cosine squared theta d theta. I'm going to send my 1/2 right through there. And while I'm at it, I'm going to send the 1/2 through there. And while I'm at it, again, nice little ending section here because we get to apply some other things from earlier in the semester. Got that cosine squared, so I'm going to send the 1/2 through, and at the same time, I'm going to use the identity to simplify that cosine squared. So we got 2 plus 8 cosine of theta plus 8 times, and then I'm going to have 1 plus cosine of 2 theta over 2 d theta. Finish this out. And maybe before I plug in my bounds, simplify just a little bit more. So I end up with 6 theta plus 8 sine of theta plus 2 sine of 2 theta. And then plugging in my bounds here. All right, now let's just plug and chug. So as we go through this, plugging in 4 pi over 3, we're going to get 8 pi plus 8 times negative root 3 over 2 plus 2 times root 3 over 2. Let's put that all in parentheses. Minus 4 pi plus 8 root 3 over 2 plus 2 times negative root 3 over 2. Okay, and that might have been a nice, right there would have been kind of the nice reasoning why we might have wanted to use symmetry or use some symmetry. Definitely plugging in pi right there might have been a little bit nicer here. And ultimately I end up with, you'll just trust me on this, I did it ahead of time, 4 pi, I'll change this back to black. Ended up with 4 pi minus 6 root 3, or approximately 2.174. And that is my area. Area of the inner loop. And by the way, just wanted to mention, the radiuses were negative right there, but this is giving me the actual area. Remember in the formula, it's 1/2 times the radius squared. So this is giving me the area that is traced out there. So even though we had, and we will sometimes have negative radiuses where we have those reflections through the origin in the polar coordinate system, but this is still giving me the actual area that was traced out and enclosed by that inner loop. Okay, want to just do one more quick example on this video, because what if we had 2 curves? So what if we ended up with 2 curves? Let me zoom out here just in case you want to take a look at that whole thing. I think we can get it all on the screen there. There we go. I'll pause right there for just a second. And then what would we do if we wanted to find the area maybe in between two different polar curves? So let's talk about that next. Okay, so if we wanted the area between two polar curves, so let's say we have two polar curves, and I just made some little squiggly polar curves here. If we had two polar curves that were running through the polar coordinate system, and we wanted to find the area enclosed between the two, between two rays, call them theta equals A and theta equals B. What we're going to do is we're going to end up looking at the area of the outer minus the area of the inner. And so we'll go over there in just a second. This is where f of theta is greater than or equal to g of theta in the scenario that we're looking at here. And so we would just compute the area if we were looking at f of theta, then subtract the area if we were looking at g of theta, pull those together into one integral, and end up with a nice little formula that says this. It says if we want, given two polar curves, the area between the two curves when f of theta is greater than g of theta, and between the rays a to b, is going to simply be the area of the integral, the area is going to be equal to the integral from a to b of 1/2 f of theta squared minus g of theta squared d theta. And that's just taking the area of the outer radius squared minus the inner radius squared. Okay, so let's do an example. This is the one I want to do, but I actually set it up over here. So let's get that up on the screen. So let's determine the area that lies inside r equals 3 plus 2 sine of theta, and outside r equals 2. Real quick, r equals 2 is simply a circle where the radius stays fixed. So r equals 2 is just this circle. I'm going to zoom in here so I can get on the actual curve. Just a circle of radius 2. So then what is my other curve? Well, let's see. So if we have 3 plus 2 sine of theta, we are going to have a curve that looks something like this. Let's do it in red over here on the polar curve. So we're going to start at theta equals 0. This was the theta, the r graph. So we're going to start over here at 3, and then we're going to be up to 5, and then back to 3, and then we're going to come into 1, and then back out to 3. So we're going to get this little heart shape. I actually want to clean that up just a little bit, kind of knowing what's happening. Okay. All right, so I kind of know a little bit about what's going to happen here. And so let's take a look at where do those two curves intersect. And in order to get the graph, we probably should have done that first, but let's do that now. So where do those two curves actually intersect? Because what we want to find is the area that lies inside of the cardioid here and outside of the circle. So where would that be? Well, I know my curve is not the greatest, but we are looking for this area here. Okay, the area inside the cardioid and outside the circle. So we definitely need to figure out what are these two intersection points. And if we had graphed in some sort of technology, we might be able to see that from the graph. We didn't do that, so here, let's do that. Find those intersection points. And we want to show where those intersection points come from anyway. So how do we find those intersection points? Well, intersection points of a curve. This is very much like working in the rectangular coordinate system, just now we're working with polar curves. So what are the intersection points when the two curves are equal? So when does 2 equal 3 plus 2 sine of theta? And that would be when the sine of theta equals negative 1/2. And so that's going to occur, of course, at our pi over 6's. Let's look at this in the right quadrants. So that's going to happen at 7 pi over 6. Oh, you know what we could also do is we could even, if we wanted to see 2 on this graph, we could see the graphical intersection points as well. So there's the graph r equals 2, and here was the graph r equals 3 plus 2 sine of theta. So we can even see the visual here. We can see where those intersection points are here and here. So we're at 7 pi over 6 and 11 pi over 6. That is in one cycle. Of course, we go back through, right? As we continue around and around, we end up back through. So we're at 7 pi over 6 and 11 pi over 6. So when I was graphing that, I just wanted to kind of get that as close as I could as I was doing the graph. Okay, so that's the 2 rays that we're actually looking at. But check out, if I were to say, right, we want to trace out this area, and we want to trace it out in a increasing order. We talked about that with that b being greater than a when we're setting this up. And so check this out. If I go from 11 pi over 6 to 7 pi over 6, that doesn't make any sense. That's how I want to trace out the area. We want to make sure that we always trace out the area. Trace out the area in increasing order of theta, right? We want to make sure that theta increases as we trace out. We can't go from 11 pi over 6 to 7 pi over 6. That would not be going in the right direction. So what we have to do is we have to think for a second about the fact that 11 pi over 6 has an infinite number of other representations. And so we could say, well, that's the same as negative pi over 6. 11 pi over 6 is equivalent to negative pi over 6. And so what we could do is we could say theta, we should go from theta equals negative pi over 6 to theta equals 7 pi over 6. The other thing that we could do, as I'm looking at this, we could also think about using some symmetry. And we could say, let's start at pi over 2 and go from pi over 2 to 7 pi over 6 and double the area. We can also use the symmetry of these polar curves. And we could go from theta equals pi over 2 to theta equals 7 pi over 6 and double the area. Okay? So we could do either of, well, there's actually lots of different ways to do it, but those are 2 of the ways that we could do it. So we could use either of those. I'm going to set it up like this, but know that you could apply symmetry and work it that way. Okay, so if we want the area then between the curves, this is going to be equal to the integral from negative pi over 6 to 7 pi over 6 of 1/2, and we're going to take the outer function squared minus the inner function squared with respect to theta. And this is going to be the integral from negative pi over 6 to 7 pi over 6 of 1/2. And our outer curve here was the cardioid, the 3 plus 2 sine of theta. Squared minus 2 squared d theta. And we could continue this on, and I'll take it just a little step further here, and then I think I'll end the video. This is then from negative pi over 6 to 7 pi over 6, 1/2, expand everything out here, 9 plus 12 sine of theta plus 4 sine squared of theta minus 4 d theta, and dot, dot, dot. At this point, this is just integration. integration strategies, and then plugging it in. It turns out, and I did write this out ahead of time, so I will write this for you. This ends up being 14 pi over 3 plus 11 root 3 over 2, or approximately, if we wanted the approximation, 24.2. This was the area enclosed. You do have to use a little identity on this guy, just like actually the previous example, and you can finish that one out. So I'm going to zoom out here and get it all back on the screen. If we were to extend this, and we could definitely extend this a little bit further and say, what if instead of this area that's inside this cardioid and outside the circle, what if we wanted the area inside the circle but outside the cardioid? It would flip the outer and the inner radius. So if we instead wanted this little piece of area that's down in the bottom, the bounds would actually still be the same, but we would be looking at flipping the functions. The bounds wouldn't be the same. We would actually go from the intersection points are the same, but we would go from 7 pi over 6 to 11 pi over 6, and we would flip the order of the two radiuses. The outer radius would become the circle, and the inner radius would become the cardioid. So these are kind of fun to think about how we work in a circular area here and follow these through. Okay, one last formula from here, because I started it off by saying we were going to talk about arc length as well. I'm not going to have time to do an example on this video, so we'll save that maybe for the class sessions. But right here, just applying that we're talking about parametric equations for polar coordinates here and the derivative. So I just captured those two pieces. Those are from earlier in this section. And turns out that arc length is actually this formula. So if we calculate the arc length just using our parametric equations, and then it ends up being a really fun little, math teachers like this kind of stuff. Ends up being like just a bunch of trig and simplification, and it boils down to this very nice little formula. I mean, we start off with, having to square these things up here and then add them, but then it works out really nicely, and we end up with just the integral from a to b. If we're looking for the arc length instead of area, it ends up just being the integral from a to b of the square root of 1 plus dr d theta, the derivative of the parametric curve with respect to theta squared d theta. And that ends up being just a nice little formula for arc length, and then we can calculate it. So we'll grab one of those and practice that in the class session, but that is the formula, and you can just plug right into that formula to find arc length. Okay, all right, that wraps up areas and arc lengths in polar curves.